Okay, everyone, we'll start the webinar. It's 4 p.m. in Australia and 10:34 in India. Firstly, I want to welcome everyone. I'm Jo Lanzaroni, the Marketing Director for Pluralsight in APAC, and wanted to thank you for your time and spending time with Pluralsight today. We all know everyone's time is valuable and precious, so we appreciate your commitment to Pluralsight. Today's topic is machine learning in the production environment, and it's going to be an exciting topic with two amazing presenters. Before we start, I just want to let everyone know that we're recording the session and you'll be able to receive the presentation post-event. And you can also ask questions via the Q&A chat button at the bottom of the screen. Please make sure that you add your email address to the questions so that if we don't get time to respond to those questions, we can respond to you after the event. Today's agenda will hear from Simmi for the first 10 minutes, sharing a tech executive's perspective on why we need to focus on tech skills and the importance to an organisation's transformation agenda and engaging customers. We'll then hand over to Janani to deliver her presentation on machine learning in a production environment. We expect this will go for approximately 40 minutes. Just power down my slides. We're excited to be hosting two amazing presenters today. Simmi from Tech Mahindra and Janani, one of our global Pluralsight authors. So I'd like to introduce Simmi to the audience. She's a global leader at Tech Mahindra, is responsible for leading full-scale transformation for the company across multiple dimensions, including profit, future skilling, digitization, automation, portfolio optimization, financial process excellence, and operations. Simmi has conceptualized and implemented multiple digital transformations using advanced technologies, analytics, RPA, artificial intelligence, cloud. Simmi has envisaged Skilling Next initiative for Tech Mahindra, and this initiative is focused on demand skilling for current and future roles. Her passion for skilling ensures continuous professional growth for her. Simmi was also recently awarded with the Women Leader of the Year at Tech Mahindra, a very prominent award. Simmi has been at Tech Mahindra for the last 15 years and in many senior leadership roles prior to joining Tech Mahindra with Dell and Interglobe. I'd like to thank Simmi for agreeing to kick off this Pluralsight webinar and share insights into why tech skills as emerging technologies like AI and machine learning are fundamental elements to a successful business transformation strategy. Over to you, Simmi. And unmute her. Simmi, you there?
Yeah. Can you hear me?
Yes, absolutely.
I think first of all, I would like to thank each one who has joined this particular webinar. It is not only that they've joined or shown an interest in Pluralsight, they have actually shown an interest in themselves. Because what we are going to talk today is really a future of the tech industry, but it's not only the tech industry, any industry in the world. I would basically say, if you can see the slides, it is very, very clearly visible. There was an era wherein we were really talking about moving from an industrialized way of economy. Whereas now today is an era where we're basically saying the new and future belongs to the AI-based economy. Now, if you would see the numbers talk itself, 21 billion in 2018 to 190 billion by 2025. What are we talking? So numbers speak in itself that there is an exponential growth visible in this particular area. Not only this, large adoption has started now because of the development in both hardware as well as in a software. It has really become possible. Because if you will go back and talk to the people who were in 1960s, they will also say the name of AI. So what is different today? The difference is at that time, we knew this is how AI can be delivered, but there was no possibility to deliver because the required infrastructure, whether it is hardware, the computing capabilities, or the storage capabilities, or now the kind of things we have in edge computing was not available earlier. And that is why AI is now, AI is here, and it's a reality today. Now let's talk about it. what is happening? Why is it so that the progress is so slow? Believe me, this progress from 21 billion to 190 billion has been identified keeping in mind that we would not have the required talent. If the talent availability comes faster, the growth you will see will be much larger and bigger and the faster over here. Talk about any research report, everyone is saying the largest problem is not having the right talent. And when we talk about talent, talent is not just a one technology skill, which is about knowing how do you do AI or machine learning. Talent is really about over here is full cycle. And that's what we call it at Tech Mahindra, a full cycle person. Now, what a full cycle person really means? A full cycle person means that the person understands from the requirement till deployment of any AI program or AI ML program, understands that journey, maybe in masters in few, but understands that end to end. Not only that, because we're talking about artificial intelligence, it cannot be just a technology game. You really need to understand the business. You really need to understand the domain. You need to understand the special, I would say, sub-verticalization of that domain. For example, if you are talking about Industry 4.0, then you have to understand manufacturing. And if you're talking about supply chain, you're predicting and doing analytics or on the supply chain, then you really need to understand the core and basics of supply chain. And at the same time, you need to have to be a great communicator because you end of the day, you're selling AI to human beings and to the human beings who do not have that high knowledge of the technology. So I would say a package in itself has to be understanding the domain, having a great communication abilities to be able to communicate to the people who are at a CXO level, and having the top technical knowledge is what really going to set you apart. Can we move to the next slide, please? Now, if you would look at it, some of you must have joined from India, and because I am based out of India, I can talk about it that this is not just that the corporates have identified it, the major governments have identified this as a real opportunity. In India, Indian government is spending exponentially in this for this particular cause. They are basically saying they will use this opportunity to develop their GDP to multifold. And lots of initiatives are being done. So that's why I'm sharing this, is just to let you know that it is real here and now. Not only industry, government is also looking at how to encash this opportunity. Should we move on? Now, I would like to share a bit of that. Okay, what are we really doing at Tech Mahindra when it comes to AI? I think it's important for you to know that how corporates are really thinking about it. Now, if you will see this picture at the left-hand side, we did talk about domain-centric. So it is important that you understand the domain. And the another thing what we are basically saying is AI everywhere, which means that it doesn't matter what do you do, whether you're talking about delivering a ticket to a customer, or whether you're talking about delivering an SAP S/4HANA implementation to a customer, or you're talking about decision support system for a customer, or you're talking about Amazon type retail. All places, what we are saying is AI everywhere, and it has to be, we are looking at it open source as an opportunity to democratize the AI. And we have several partnerships and collaborations. We believe that this is not a one-person game. Everyone brings in a lot of, I would say, specializations. So we have collaborations to really disrupt in this particular market. collaborations, not only with startups, collaborations with our customers, collaborations with very large alliance partners like SAP or Google to really help us be there in this particular market and delivering and helping our customers deliver, run their business better, change their business, and grow greater. This is not enabling customers in faster time to market, not only saving cost, but faster time to market, which is growth, is equally important today. I think that's what I would basically say. This is how Tech Mahindra has democratized the AI. Our platform, which is Gaia, is an open source AI marketplace. Even you can go and create your own, I would basically say, models, prediction models, AI models at that particular platform. So it is open for all, open source marketplace, which is where we are really developing the industry readiness for this particular new I would say opportunity, which is there in front of all of us. Yeah, could we move to the next slide? Now, as all of you are over here in terms of learning, so I thought I'll share with you within Tech Mahindra, this learning is a very, very high objective of all of us. And we call it upskilling as a service. Upskilling as a service is a platform which Tech Mahindra has. It's an inbuilt platform, a skill marketplace, and it has finally engaged with platforms like Pluralsight. What we do is we curate the best content from the places like Pluralsight and the other competes of Pluralsight and identify which is the best and make sure that it gets available to our associates when they need it in an interactive manner with the context and today's world of hyper-personalization is being taken care. When we are talking about AI ML roles, what we have really done is in the organization, we have identified these 6 roles which are visible over here as direct AI ML roles. But there are other roles wherein AI ML skill as a basic is needed. So for us as an organization, we call AI 101 or AI 201. AI 101, which is basic, is mandatory for every associate in the organization. Yes, every associate, each associate in the organization. That means we believe it is so important that you would not be able to do your today's job without knowing AI. So it's not just these 6 roles. It is to be successful in the world today. This is basic, like I would say Microsoft Word or Microsoft Office, maybe a few years before. That's how I would say it's so important. I think with this, I would like to hand it over to the team back and highlight that to me, AI is here, AI is now. It's important in whatever role you're playing, whether you want to just get the knowledge or whether you want to make a career, both has immense opportunities.
Great, thank you, Simmi. That was fantastic and really appreciate your perspective on things. And upskilling as a service sounds like a fantastic opportunity for staff at Tech Mahindra. So thank you for that. I'd also like to ask Janani to load her slides into the system, and I'll do a quick introduction of Janani. Janani is a master's degree from Stanford and has worked for Google for 7+ years. And she's one of our original engineers on Google Docs and holds 4 patents for its real-time collaborative editing framework. After spending years working in the Bay Area, New York and Singapore, at companies such as Microsoft, Google and Flipkart, Janani finally decided to combine her love of technology with her passion for teaching. She's now the co-founder of Lunicorn, a content studio focused on providing high-quality content for technical skill development. Lunicorn is working on developing an engine to automate animations for presentations and educational content. A special point to note is Janani is one of Pluralsight's most famous authors. She has 118 courses on our platform, which is a pretty amazing feat. Thank you, Janani, for sharing your expertise with Pluralsight and customers and with the greater APAC community. Thank you. Over to you.
Thank you, Jo. I hope everyone can hear me. And thank you, Simmi, for everything that you had to share. Now, I'm going to get started here today. I'm going to take you back in time a little bit. Not very far back in time, only about a year or so ago, around the same time last year. Here is what the SoftBank CEO, Masayoshi Son, had to say about artificial intelligence. AI will completely change the way humans live within 30 years. Here is another quote from the same article. The diseases that we could not solve in the past will be cured. Pretty ironic considering all that's happening in the world today. Well, what can one do? Reality bites. And reality bites not just predictions that Masayoshi Son has made, but it also manifests itself in other examples. Let's take a look at another headline here from the Wall Street Journal. The AI startup boom raises questions of exaggerated tech savvy. Now, this article refers to the general phenomenon of artificial intelligence and machine learning not really living up to the hype that it has generated. Now, in the context of this article, the writers of this particular piece have researched the particulars of one specific company called Engineer.ai. Now, Engineer.ai claimed to have built software and an artificial intelligence system that allows anyone to build custom software like ordering pizza. Their whole idea was that they completely democratized the process of mobile and web app development. The company claimed that all app development is essentially putting reusable components together. So they had this artificial intelligence platform, this is their claim, which basically automates by putting all of these components together, and 80% of the tasks involved in mobile app building, it's done by this platform with just 20% manually performed by their engineers. Now, this allowed them to deliver their technology very quickly to their client. Now, this was the hype. What exactly was the reality? Documents reviewed by the Wall Street Journal and several people suggest Engineer.ai doesn't use AI to assemble code for apps as it claims. In fact, they indicated that the company relies on human engineers in India and elsewhere to do most of that work. Unfortunately, we have anecdotal evidence to prove that this is not an isolated incident. This happens over and over again. And a fundamental reason for this is that startups can raise huge amounts of funding in the hundreds of millions of dollars based on prototypes, just ideas, or even the founders' personalities. But established companies that are past their IPO, well, they're held to a much higher bar. Such companies need to actually launch their products. The products have to be accepted by clients. People have to pay money, cold hard cash for these products. Revenues have to come in. Private markets, such as VCs, love funding moonshots. Public markets, well, they tend to be much more hard-nosed. Now, this is the reality which has come back into people's consciousness, and there are indications that the pendulum has now swung in the other direction. Old-fashioned profit-maximizing companies are back in vogue. Here is another headline from the Wall Street Journal. Our IT is so good, let's sell it. Old-fashioned firms that have been developing software iteratively over years are finding new ways to monetize their products. In fact, this is how AWS was born. If you think about it, Amazon had all this extra infrastructure which they had kept around to have during spike periods. They had this additional capacity which they weren't using most of the time, so then why not monetize this? This is how AWS was born, and AWS is today a cash gushing machine. So at this point in time, old school software development is back in vogue. So the question now before us is, was this artificial intelligence machine learning phenomenon all just hype? Well, The jury is still out on that. It'll take time to tell. But in my opinion, AI and ML models can be game changing for any organization, as Simi has proven just before me. However, as engineers, we need to deal with the realities of deployed models. Models that have been deployed to production encounter problems that are not apparent in the training and the model building phase. And an important reason for these problems has to do with how model building is different from software development. It's a tale of two life cycles. Software ages like wine. Models age like milk. In other words, software tends to get better after deployment, after it has been out in the wild for a while. But models degrade in quality as soon as they are deployed. And it is this fundamental misconception that often leads to errors during model building and deployment. You need to understand that software and models are very different, even though it's software engineers who are doing a lot of the model building these days, though there are statisticians and data scientists and other specialists involved. So what's the life cycle of software? This is something all of us are familiar with. We know that you develop software iteratively, you run tests on software, you fix bugs. This means that software that has been around for a while is far more robust than software that has just launched. More bug fixes have been applied, there have been more patches, all code paths have been tested, usability fixes have been applied, which is why software which has matured for a while, well, people love it because it works as they expect. External changes rarely affect regular software. Your client wants a new feature, well, you iteratively add a new feature and you launch that feature as a part of your next release cycle. So software can have steady periodic release cycles. Now, this life cycle of software does not apply to machine learning models. A model, in fact, has its high point just before you deploy to production. So you've tested your model, you've had all this training data, you've tried your model out on different circumstances, you feel good about your model and you launch it. But really, that is the pinnacle. You're doomed for disappointment if you assume that deployed models will work as well in production as they did in testing. This is because static machine learning models become less useful over time. What exactly is a machine learning model? Well, it's something that tries to recreate reality and you use the model to perform predictions. But reality keeps changing, and if your models don't keep up with those changes, well, they're not going to work as well as you expect them to. Model development is not the same as software development. Models need a constant stream of new data to keep them working well. Relationships in the real world are dynamic. They keep changing, people's tastes change, people's preferences change. And if your model is not constantly being updated to reflect these changes, well, your model doesn't reflect the real world. So models need to adjust for shifting realities in the real world. In fact, deploying models to production is just the beginning. The way I think of it is when you deploy a model, that's like giving birth to a child. We all know that things just start there. It's not the end. You still have to nurture your children, bring up your children, send them to school. You still have to deal with the teenage years. Deploying models is just the beginning. And once you understand that, well, a lot of things will start making sense. So where are we at today? We know that models are performing well in the lab. When you prototype your models, they seem amazing, but they don't perform well on the production line. Now, before you go ahead and give in to your disappointment, before writing off machine learning and artificial intelligence as hype, try these three simple steps. So I'm going to offer you three simple solutions. They're simple conceptually, but they're of course all in how you implement these solutions. The first of these simple solutions has to do with how you train your model. Now, it's quite possible that the model that you have is fairly complex, but you don't have very much training data, or your training data is sparse. This is what can lead to your model overfitting on the training data, and an overfitted model does not do well in production. So there are plenty of techniques available in the real world to mitigate the effects of overfitting, and we'll discuss some of these in detail in just a bit. The next simple solution is in how you handle real-time data. Now, when you're training your model, your training data is present on a file system somewhere, or maybe it's in a data warehouse. But once your model is deployed to production, it's performing prediction on streaming data, real-time data that comes in for which you need predictions almost instantaneously. You need to ensure that your batch and streaming data don't follow different code paths. And finally, the third simple solution has to do with what you do once your model has been deployed. Make sure you babysit your model after deployment. Don't just move on to the next cool problem. There is a lot of work still to be done to keep your models performing well. So these are the three simple solutions. Let's talk about some broad categories of problems that afflict AI-based solutions today. Now, there are, of course, an infinite number of problems that could beset your model. I'm not trying to cover all of these here. Here are 4 broad categories of problems, and we'll discuss what the problem is and the solutions that you can use to mitigate their effects. Overfitting, training, serving skew, concept drift, and concerted adversaries. We'll start off by discussing what exactly overfitting is all about and how you can mitigate the effects of overfitting. So this is the first simple solution that I referred to just a minute or two ago. All right. So what exactly does it mean when your model has overfit on your training data? Let's take a very simple example here. I'm going to use a 2-dimensional coordinate plane to represent my data because that's easy to visualize. Let's say the x-axis represents the predictors that you feed into your model, and the y-axis represents the target or what you're trying to predict using the model. So here are all of the points that represent your training data. The objective is find the best curve through these points. That curve will serve as a model that we use for prediction. So what you're looking to do is find a curve where we feed in x values and it'll give us the corresponding y value. All right. Now you can see this curve. That seems like it's a good fit on these data points, but how do you objectively measure a good fit? A curve is said to have a good fit if the distances of all of your data points from the curve are small. This is an objective way to measure this. This is what linear regression is all about, by the way. It's not a curve, but that's a line, but the same idea. What about this curve here? This curve passes through every single data point. Would you call this a good model? What is a good model anyway? Will it perform well on test data? A model is good when it performs well on unseen data, when it performs well on prediction instances that it hasn't encountered before. The curve that we have here, well, it passes through every single point in our training data, but I wouldn't really call it a good model because it really won't work well when you apply this model to test data for prediction. And this is a classic example of an overfitted model. It's simplified so that it's easier for us to visualize, but this is what it means to have an overfitted model, a model that has great performance in training. So you've run the model, trained it on your training data, it has a very good accuracy. If it's a regression model, it has a great R-square. You're very happy with your model, but this model has a poor performance in real usage. It doesn't really work well on test data, instances that it hasn't encountered before. In fact, if you'd gone with a simpler model, a simple straight line, for example, it may have worse performance in training, but it's probably better for prediction. So simplifying your model often leads to a better model when used for prediction. So this is something that might seem counterintuitive, but it happens to be true. So to summarize, an overfitted model is one which has a low training error. The model does very well in training, but it has a high test error. The model doesn't work well with real data, doesn't work well once you've deployed it and you're using it for prediction. So it has to do with how you're training your model. So how do you mitigate and fix the effects of overfitting? How do you prevent overfitting? There's one more. Conceptually, An overfitted model is one which has memorized your training data, but it hasn't found general patterns in the data. You want your machine learning model to extract significant patterns in the underlying data, but you don't want it to memorize the data, because memorizing the data doesn't really help when you have new data to work with. So this model's ability to adapt to new unseen data is poor. So how do you prevent overfitting? Here are 4 broad techniques that you can use. The first of these is called regularization, and this is typically used with regression models, simpler models. This is where to the objective function, while you're training your model, every model has an objective function that you try to minimize. You add an additional penalty term which penalizes complex models. This additional penalty term, essentially what it does is it tries to keep your model's parameters simpler. It forces your models to keep things simple. So that is regularization. Another way you can prevent overfitting is by the use of cross-validation. So you have distinct training and validation phases. So you have your training data. You'll use only a subset of your training data to train your model, and the remaining part of the training data you'll use to validate your model. And you do this in multiple iterations. So that is cross-validation. So you only pick that model that does well on validation data. Then if you're working with neural networks, a technique that you can use to prevent overfitting is dropout. This is where you intentionally turn off certain neurons during the training process of your neural network. If you deactivate certain neurons, it forces the other neurons in your neural network to learn more from the data. And a 4th technique is ensemble learning. This is where you say, one model, really, I'm not sure it will perform well. What I really want is to train a number of different models using different algorithms, so they learn different things from the data, and the final output that I'll use will be an aggregation of all of the individual models. So the individual models together make up an ensemble, and the prediction that you'll use will be the output of the ensemble. All right. Regularization and cross-validation, they're fairly straightforward. Let's talk about how a dropout works with neural networks. And we'll visualize this so that it's easy to understand. Now, hopefully all of you here today are familiar with how neural networks work. The active learning unit in any neural network is a neuron. Neurons are arranged in layers. So you can see these layers represented here. And neurons in one layer typically receive the output from a previous layer. They perform some kind of mathematical function on the input that they receive, and they pass their output on to neurons in the next layer. Now, neurons in every layer are interconnected with other neurons, and the model parameters for your neural network are essentially the weights associated with the interconnections that you see. Now, if you have a densely connected neural network, that means you have many, many interconnections between your neurons. So that means you have a huge number of model parameters that you need to train. When you work with densely connected neural networks, there is a high risk of overfitting on your training data. You're trying to learn too much from your data. And the moment you try to learn too much, well, your neural network will start memorizing the data instead of extracting patterns. So you need to constrain your neural network in some way to extract significant patterns. So when you have this high risk of overfitting because of this dense complex neural network, what you'll do is in every iteration of training, for every epoch of training, you'll turn off certain neurons. And how many neurons you'll turn off is based on this dropout percentage that you specify. This is something that you can configure. Let's say you've chosen a dropout of 50%. This means you'll randomly switch off 50% of the neurons in each training step. So maybe for one training step, this is what your neural network looks like. So half the neurons are not learning anything. The other half are forced to learn patterns in your data. It's kind of like in an office, if you say 50% of the individuals will not show up for a week, then the other 50% is forced to pick up slack, but that makes them learn more about maybe, other things that people do within the organization. That's exactly what dropout tries to do. So for every iteration, you randomly turn off a different 50% of the neurons. So all of the neurons are involved in training, but at different points in time. So every training step will build a different configuration of your neural network, as you see here. And finally, once training is complete, during the prediction phase, you'll use all of the neurons. So dropout applies only during the training phase where you're forcing different neurons to learn new things from your data. But during prediction, you'll use the entire neural network. All of the neurons will be active in order to perform prediction. So this is dropout. Let's move on to discussing how ensemble learning works to mitigate overfitting. Ensemble learning is a machine learning technique where you feel that one model alone is not sufficient to learn all of the patterns that exist in your data. You have several learners. Here, learner refers to a machine learning model. Several machine learning models are combined to obtain a better performance than any of the learners individually. All right. Now, here is the data, and you want machine learning models to fit on this data, maybe to perform regression, maybe to perform classification. It can be any of the machine learning techniques. What you'll do is, instead of training just one model on this data, you'll train many different models, many different predictors, and the predictors should be diverse in that they should be very different from one another, so they learn different things from your data. This is the basic idea behind ensemble learning. So when you're performing ensemble learning, there are three important questions that you need to ask yourself. The first is, what kind of individual learners to use? What are those individual machine learning models that make up your ensemble? The second question is, how should these individual learners be trained? Are you going to train them all on the same data set? Are you going to use a subset of data for each model? How does that work? And finally, once all of your individual models have been trained and you're using the ensemble for prediction, how will you combine the predictions from individual models? So these are three important questions that you have to consider in ensemble learning. Let's start off by discussing what kind of individual learners you ought to use. Now, the individual learners or the models that make up your ensemble can be of any type. It's not that there is some kind of constraint. So they can be traditional machine learning models like support vector machines, decision trees, regression models, some kind of naive Bayes. It can be any kind of model. Individual learners can also be neural networks. But in order to make the most of ensemble learning, each learner should be as different as possible from other learners, because you want the individual models to extract different bits of information from the underlying data. That is the objective. So if you have all of your learners be logistic regression models, well, that's not really going to help, because it's going to extract the same information over and over again. You want different viewpoints on the data. So it's quite common to use decision trees as individual learners, because it's possible to have very different decision trees based on what subset of data you use to feed and train individual decision trees in your ensemble. So decision trees are commonly used within ensemble learning. If you've heard of a random forest regression and random forest classification models, well, these are ensemble learning techniques that use decision trees. All right. The next important question is, how should individual learners be trained? Now, there are two ways to approach this. Remember, you want every learner to learn something different from your data. So if the learners themselves are different, if you're using a logistic regression model, a support vector classification model, and then maybe a naive Bayes model, so your models themselves are different, they can be trained on the same data set. Because the models are different, they'll extract different information from the data. But if you're using similar learners, let's say you're using all neural networks or all decision trees within your ensemble, then there are two choices available to you. Each model can be trained on random samples of training data. So you don't use the entire training data set to train your model. Instead, you'll have the first model train on maybe the 80% of the training data picked randomly. The next model will be trained on another 80%, again picked randomly. So they're never looking at the same data points. So the models will end up being different. You can also configure it to have every model trained using a random set of features. So if you have 20 features or 20 predictors which are part of your model, then maybe you use 5 predictors to train one individual learner, another 5 to train another individual learner, and so on. So this way, your models will extract different bits of information. This brings us to the third question: how should the output of individual learners be combined? So you've finished training all of your individual learners in your ensemble, and now you're ready to use your ensemble for prediction. So a new problem instance comes in. This is what you need to perform some kind of prediction on this problem instance. You'll feed this problem instance in to all of the individual learners. You'll tell every individual learner perform some, give me your output for this problem instance. So every individual learner will give its own prediction. Let's say it's a classification model of some sort. Then you need to have some kind of technique that you use to combine the ensemble's prediction to get the final output. So you need a way to combine the predictions of the input of the individual models to get your final prediction. Now, there are many techniques that you can use to combine the individual learners to get the final prediction of the ensemble. One is hard voting. This is a simple majority vote. So for classification models, you'll basically poll all of the individual learners. Whatever the majority classification category is, that is the output of the ensemble. Soft voting is when you use some kind of probability weighted average. So every individual learner makes an output prediction with some kind of probability. You use that probability to average out all of the individual learners' prediction to get the prediction of the ensemble. You can also make things even more complex and use a technique called stacking. This is where you'll feed in the outputs of the individual learners, the predictions of the individual learners, into another machine learning model and have that model make the prediction. So all of these ways are available to you for combining individual learners. All right, this completes our discussion of mitigating the risks associated with overfitting. Let's move on to training serving skew. This is the simple solution that we spoke of earlier, where you need to handle real-time data correctly. Once again, this is easier said than done because this might involve significant changes based on how your training process and your prediction process has been set up. But conceptually, it's simple to understand and it makes sense. When do you know that your model is probably a victim of training serving skew? You find that your model performs very well in backtests. Even with validation data, it seems to do really well. But once you've deployed to production and you have it work on real-time data, it doesn't do that well. This could be because of training serving skew. So what exactly does that mean? Now, when you're training your model, the data that you used is typically data that your organization has collected. It's present on a file system somewhere. Maybe it's in a data warehouse. Maybe it's in a database. This is all batch data. All of the data is available up front in some kind of persistent storage. You'll typically have a pipeline which sources this batch data, and you'll have a bunch of transformations that you apply on this batch data. Training data is normally sourced from batch pipelines and processed meticulously well. You've spent a lot of time on the training process, so it's quite likely that your processing is perfect. But when it comes to prediction data, now you're eager to get your machine learning model deployed to production, right? And prediction data is real-time streaming data. Have you paid the same meticulous attention to your streaming pipeline? Maybe not. It's possible that you have done so, but it's possible that you haven't. So it's quite possible that your prediction data is processed in an ad hoc manner, and you've taken many shortcuts to kind of get things working. And this is what results in training serving skew. So you need to ensure that batch and streaming data should be processed in the same manner, using the same pipeline. Whatever transformations you apply to your batch data, you should have the same set of transformations applied to your streaming data. Now, there are several architectures which bring together batch and streaming data pipelines. Lambda and Kappa architectures are two most famous ones. Both of these serve to integrate batch as well as streaming data, but they do so in different ways. Now, Lambda architectures tend to be more robust, but it couples batch and streaming pipelines less tightly. So here is kind of an architecture diagram of how you might set up your Lambda architecture. You can see that a lot of the technology that I've used here, These are components that are part of the Google Cloud platform, but there are equivalents for any cloud provider, whether it's Azure, whether it's AWS, or some other platform, even in the open source community. So you have streaming data and batch data at the very left of this diagram. Streaming data is fed to a speed layer. Batch data is fed into a batch layer. All of this combines together to a serving layer. Now, in the Lambda architecture, batch data is the source of truth. So you're basically storing your streaming data in some kind of intermediate persistent storage. Then it becomes batch data. Then you process both of the data in the same manner. That's the idea behind Lambda architecture. So streaming code may also be stored in the batch layer. Now, Lambda architecture typically requires that you have a different code base for your batch data as well as streaming data, and it's kind of up to you to make sure that you have reusable components across the two and you're performing the same processing. Okay, but Kappa architecture is the integration is even stronger between batch and streaming. Stream is the source of truth. Typically, Kappa architecture is implemented using technology which retains a log of all of the data. So your streaming data is stored in logs. Your batch data also has logs associated with it, and you always process from the stream. So you use a single processing framework to process both your batch as well as streaming data. So here is an architecture diagram of how your Kappa architecture might be set up. It's fairly simple, not too many complicating factors. So you have batch data and streaming data. Both of these are fed into the same data flow pipeline for processing. So you use the same code to process both. So maintaining one code base, well, it reduces the burden on engineering. I mean, even though there might be an initial investment for this, but also in the long term, it will serve you well because whatever changes you make to that pipeline will apply to batch as well as streaming data, and you'll eliminate training serving skew. So training and prediction data ought to follow identical code paths. Let's now move on to discussing concept drift and concerted adversaries. Now, both of these are problem categories which have the same solution. Babysit your model after deployment. Don't just move on. Your work is not done. There's a lot left to do. Let's talk about what concept drift means first. Now, anytime you have a machine learning model that you've trained on your data, what you're essentially trying to do is figuring out the relationship that exists between your output or your target, that is the Y variable, and the X variables, which make up your predictors. So the relationship between the features, that is the X variables, and the labels, that is the Y variables, well, this relationship will change over time. Machine learning models that fail to keep up with the dynamic nature of this relationship, well, won't perform well. So concept drift happens because the world is constantly changing. Relationships that you're trying to model from the real world, they are dynamic and not static. And if your model is not keeping up to date with these relationships as they change, well, this is the most important reason why your model quality degrades as soon as you deploy your model. This is why rule-based systems are not in vogue anymore, because you simply can't have manually generated rules that keep up with the dynamic nature of relationships in the real world. So why does concept drift occur? Well, there can be many reasons. Concept drift is typically related to regime changes or structural breaks in statistics. For example, you had a bunch of mathematical and quantitative models modeling the stock market just before the financial crisis hit, maybe about 10 to 12 years ago. Well, within 6 months, all of these models were obsolete, or maybe within a month, the underlying assumptions changed. And if the models were not picking up on these changes, well, they were useless. So you need to keep monitoring and retraining deployed models. How fast do you need to do this? Well, it depends on your use case. For some people, if it's for fraud detection, it probably has to be done really often because there are always hackers coming up with new ways to hack your system. Another solution is it might be that your model just can't keep up. You might need to redevelop your models from scratch if retraining is not enough. Okay, let's visualize how this concept drift might work. Let's say you have two axes and you have reviews, maybe for a movie. So you have the time when the review was posted on the x-axis and the number of words in a review on the y-axis. And you need to classify reviews as negative or positive. Now, let's say we have a very simple model that draws a decision boundary between positive and negative review. So the original decision boundary looks like this. This is the decision boundary your model had at the time of deployment. Okay, because this is the data that you had to work with. Now it's quite possible that new instances come in and you're classifying new reviews using this model. Now these new instances are new data points that are available. And here you can see that these are the data points that have been misclassified by our model. Positive reviews classified as negative and vice versa. Now your model needs to stay up to date with these new data points. The decision boundary needs to change. The model needs to be updated. This is concept drift. So concept drift can occur when the data itself changes, so your model needs new data. Concept drift can also occur when our interpretation of the data has changed. If the way we analyze data is different because of the different realities that exist in the real world, that can also result in concept drift. So concept drift, the way you mitigate this is by constantly monitoring and retraining your deployed models on the new data that comes in. All right. Let's move on to concerted adversaries. Now, you might have machine learning models for different use cases, and typically these systems tend to be critical, which is why you're looking for machine learning for a solution. Can be fraud detection, fake news detection, quantitative trading. These are just a few examples. Now, for whatever you try to do, you have adversaries who are trying to thwart what you're trying to achieve, who are trying to mislead your models to making the wrong classification for some kind of personal benefit. Or, that's just, there are people out there trying to bring your models down. They are trying to confuse and mislead your models. Well, there's maybe nothing you can do about it except maybe retrain your models, but there's also another solution that you can try. Large companies often have human minders for their machine learning models, especially for critical systems. Human minders are basically, they go in and look at all of the data that the model classified incorrectly, got wrong, and they try and label them so that it's available for training the next time around, but they also try and analyze why their model got it wrong. So you need humans to thwart other humans. At this point in time, machines are not smarter than humans for this particular use case. So we are back to the future. From machine learning, we've gone back to manual learning in order to improve our machine learning models. So thwarting concerted adversaries requires continuous manual learning to complement machine learning. So here are the 4 problems that we discussed: afflicting AI-based solutions. Here are the 3 simple solutions to our very complex problems. Of course, implementing these solutions will require a lot of work. That's by no means simple. Now, if you're interested in all of the concepts and techniques that I covered here in this talk, here are some courses that you can watch in Pluralsight: employing Ensemble methods, image classification, natural language processing, and deploying machine learning solutions. So I think I finished just on time. Can do a little bit of Q&A.
So, is there any questions? Where are they? Thanks, Janani. That was great work. We've got some questions here online, and I'll just read them out. And then if you wanted to answer them as well too.
Sure.
What if when we have trained the different models with random data, the models were working properly, but when combined, the prediction is not good?
So it could be anything. It really depends on your use case. The categories of problems that I covered are the ones that are most common and which are still being researched. So you could see whether the way you're processing your prediction data and training data, if that's different, that's an easy way to check upon things. When the prediction is not good, one way is to use your prediction instance to retrain your models. Maybe something has changed. Maybe you're predicting on different kinds of data. So I'm hoping that some of the categories of solutions that I discussed here will help you debug this.
What is a simple one at the beginning of the presentation? What is the difference between machine learning specialist and data science roles?
I think this was for Simmi. It was on her slide.
We'll have to get back. We'll have to get. We'll have to get back to that one with Simmi and get you an answer as well too.
Yeah.
Next question.
During batch processing, there's a process of batch normalization. For stream processing, is there any process? You can use the batch normalization parameters that you got from your batch data on your streaming data. That's definitely, like, you'll save the parameters. So you have parameters across batches. Maybe you'll average these parameters across multiple batches, and then you use the same parameters for your streaming data. That is one way to go about it. The other thing would be, make sure that whatever streaming data you get in becomes a part of your batch training. So that way you're incorporating the information present in your streaming data back in your training process. Then there's one, how do you balance imbalanced data? Now, there are many techniques out there. And right now, because there are different sampling techniques, maybe like the oversampling, undersampling, and there are specific techniques for oversampling and undersampling that allow you to balance imbalanced data. I'm not able to recall the names of those techniques right now.
Thank you, Janani. I've learned a lot about video lectures on Pluralsight. So thank you. There's one more down below, which is a best way of data processing, cleaning process.
And by the way, I should say Rajat has just given you an answer for one way to balance imbalanced data, the SMOT technique. That is a specific technique for you to, I think, oversample your training instances for which you have few samples and get a more balanced data set. Thank you, Rajat. Shigoel has said, best way of data processing, cleaning process. There isn't one best way, because really data cleaning is really dependent on how your data is dirty. So they can be missing values, they can be outliers. I can suggest a few techniques. Like with missing values, then you have to make a choice. Can you just eliminate the records with missing values? Maybe not, if you don't have sufficient data. If you have a large data set, maybe you can just eliminate those records. But let's say you can't eliminate those records, then you have to have some imputation technique that you use to fill in missing values. Maybe you fill in missing values using the average of the data set or the median of the data set, or you can build a machine learning model to predict the missing value. All of these techniques are perfectly legitimate. If you're dealing with outliers, you'll need further exploration as to why this data point is an outlier. It can be because there was something wrong with your data collection. It can be a legitimate outlier, in which case you want to include it and have it be part of your model. If you feel that your outliers are not legitimate, you can use, let's say you're performing regression analysis, you can use a different regression technique which will mitigate the effects of outliers, like robust regression. So all of these are options. There is no one solution, unfortunately. And that's what makes all of this data pre-processing so hard. So.
Question from Chita, I think, Janani, one about human intervention. Can you comment on that one?
Yes, as a last step, I'm not saying human intervention is the only answer. The whole idea is, if you're retraining your machine learning model using whatever new data you get in and you correctly label your new data, well, that is the first step. So that way you're getting your model to adjust as the data changes. So that is absolutely required. Now, human intervention is kind of needed for like these you need someone to monitor the models. And humans are the best available option at this time. It's not the only way, but it is a way. And often as engineers, you don't want any human intervention, right? You want everything to be automated and nicely set up, and that makes us happy. It makes me happy as well. But sometimes you have to realize that human intervention may be needed, and that's just to know that this option is out there. Please give us the list of courses available on Pluralsight that you mentioned in your last slide. And Rajat has come up with some other scaling techniques that you can use to work with outliers. Min-max scaler, there's the max ab scaler. All of these are legitimate. They are very, very sensible. List of courses available on Pluralsight that you mentioned in your last slide. Vishal, can we just share this? I don't know, Joe, can we share this with the PDF with attendees?
Yes, we'll, as part of the follow-up, we'll share with everyone opportunity to listen to the recording with access to Pluralsight courses that relate to this topic and to your topics as well too, Janani.
Maybe I'll answer one or two more questions. How do we treat outliers? How much data can be dropped? That's the whole issue with machine learning. There is no one hard and fast answer. How do we treat outliers? You look at why outliers exist. Is it because of some error in how you've recorded your data? In that case, most definitely go ahead and drop those outliers. You can just replace the outlier values with, say, the mean or median for that column. How much data can be dropped? Well, you want to drop as little data as possible, in my opinion. If you have a huge data set, if you lose a little bit of data, it doesn't matter. But if your data set is small to begin with, you want to retain as much of your data as possible. So there is no one answer, unfortunately.
All right, Janani, I think we'll leave it there because we've
okay.
Sort of 10 minutes over the webinar, and I know people have allocated an hour to attend this session. Really wanted to thank you for your expertise and knowledge on this subject, and just the simplistic way you presented it initially and then grew into the challenges that you see when you're in a production environment. So I think it was a fabulous demonstration of your knowledge and skills. So thank you. And thank you to all the attendees who've attended today's presentation. We really appreciate your time and look forward to connecting with you post-event. Thank you, everyone.